Hey guys, this is part 6 of the series on energy-based models. In this video, we are going to train an EBM to generate images from noise. To train the model, we will use the classic MNIST dataset of handwritten digits. Each image is 28 times 28, which is a total of 784 pixels. That means each row of the dataset or each configuration of our system is a vector living in a 784 dimensional space. If you remember the last video, our toy example lived in just one dimension. As a result, we knew the value of the partition function z and hence the complete form of the probability function. That allowed us to generate samples out of the probability distribution and use a direct Monte Carlo method to compute the model expectation term. That direct Monte Carlo is no longer possible. Here's the reason. The partition function z is now an integral over 784 dimensions. To give you a sense of a scale, even a laughably coarse grid with just 10 points per dimension would require 10 to the power of 784 evaluations. That is more than the number of atoms in the observable universe raised to roughly the 9th power. So we will try another method. First, the energy function u of theta will be a neural network that takes an image as input and returns a single scalar, which would be the energy u. Second, the data side expectation is estimated by averaging over mini batches of real MNIST images. Third, the model side expectation is estimated by averaging over samples generated with the Unadjusted Langevin Algorithm, or ULA, initialized from a persistent replay buffer of past samples, with a small fraction of chains restarted from pure noise at every iteration. Don't worry, I will explain all this during the video. And fourth, during the training, the parameters follow the gradient of the cross entropy, which is just the data side expectation minus the model side expectation. Now that we have an overview, let's build this step by step. Step 1 is to load MNIST and look at the data. Here, we normalize the pixel values to the range from -1 to 1. The reason is that the Langevin sampler, which we will discuss later, will move randomly around in pixel space, and it's convenient to keep the physical region of configurations centered at 0. In this code, we set up our configuration, load the MNIST training set, and use a data loader that hands us shuffled mini batches. Here, we look at a few images in the dataset. Each of these images is one low-energy configuration of our system, in the same sense that a snapshot of the gas container from the beginning of this series was one configuration of that system. The step 2 is where the energy function becomes a neural network. In the 1D toy model, the energy had a fixed analytical form with only 2 free parameters. For images, we let a small convolutional network be the energy function. It maps an image from the 784-dimensional space to a single scalar being the energy. An important point to note is that we use a smooth activations SiLU instead of ReLU. The reason is that, as we will see below, the Langevin sampler needs the gradient of the energy, and a smooth energy landscape gives much better behaved gradients. In this cell, we implement the network with a few convolutional layers, then flatten it and pass it through a couple of linear layers to get a single scalar. This network has about 187,000 free parameters, and those parameters are our theta. Now, before any training, the network knows nothing, so real digits and pure noise should have statistically indistinguishable energies. We verified this by taking a batch of real digits and a batch of random noise, computing their energies, and plotting the two histograms. And as you can see, the two histograms overlap fairly well. The entire goal of training the EBM is to separate these. Real digits must sink to low energy, and everything else must push up onto the heels of the energy landscape. Step 3 is the Langevin sampler. To estimate the model side expectation, we need samples from the model distribution. Since we cannot compute z of theta in our extremely high dimensional space, we need to draw samples without ever knowing z. To do that, we use Markov Chain Monte Carlo methods, and a particularly popular one, since our pixel values are continuous, is the unadjusted Langevin algorithm, or ULA. Let me first explain how to use the ULA method, and then I'll explain where it comes from in physics. Here's the recipe. We start from a randomly selected point in pixel space, which is an image with random pixel values. This will be our first sample, and we label it x0. Here, the index refers to a time step and also to a row of the sample dataset that we want to generate. We then generate the next sample using the update rule. X at a step k plus 1 equals x at a step k minus a step size h times the gradient of the energy at xk plus the square root of 2h times an independent Gaussian noise. To find the first sample, x1, we plug x0 into the right-hand side, then we plug x1 back in to get x2, and we repeat this loop for as many times as our computation budget allows. That gives us a sample dataset with which we estimate the model side expectation simply by replacing the interactable expectation with the empirical average over these generated samples. Now, an important note. The recipe of maintaining these chains across training iterations is called persistent contrastive divergence, or PCD. A chain started from a random configuration needs a very long time to converge. This is called the mixing time. And we simply cannot afford thousands of Langevin steps inside every single training iteration. The classic shortcut, plain contrastive divergence, initializes the chain at real data points. That makes the chain converge quickly, but it has a serious hidden flaw for generation that we'll discuss in step 4. The samples barely move away from the real data, so the two expectations in the gradient cancel and training stalls. PCD takes a different shortcut. Instead of restarting chains at the data, we never really restart them. We store the final samples of each iteration in a buffer and use them as the starting points of the next iteration. So each chain keeps mixing across the whole of training. Now, let me explain the derivation of the unadjusted Langevin algorithm, or ULA, from physics. The key fact is that the ULA update is just a discretization of the overdamped Langevin diffusion, which is the equation from statistical physics that describes the position of a particle immersed in a viscous fluid, subject to a force field that pulls it downhill on the energy landscape, while random thermal kicks from the fluid keep it exploring. In thermal equilibrium, such a particle is distributed according to the Boltzmann-Gibbs measure, which is exactly the model distribution we want to sample from. The diffusion equation says that the change in position of the particle is minus the gradient of the energy times the increment of time, plus the square root of 2 times a Wiener process increment. To see that its stationary distribution is the Gibbs measure, we look at the Fokker-Planck equation that governs how the probability density evolves. If we substitute the Gibbs measure into the right-hand side, the drift term and the diffusion term cancel exactly, so the density stops changing. And under mild conditions, the diffusion not only preserves this distribution, but also converges to it from any initialization. So for a large number of samples, they are approximately distributed according to the model. The crucial point is that the update rule only involves the gradient of the energy. Therefore, the normalization constant z never appears because it is killed by that gradient. This is precisely what lets us sample from the model without ever computing z. In other words, since our dataset has the same distribution as the particle in the fluid, its samples relate to each other exactly the way the particle's positions do. We also add 2 small engineering safeguards in the code. These don't change the algorithm. They just keep the chain from blowing up early in training when the energy landscape is still wild. We clamp both the gradient values and the samples back into their valid ranges after each step. In the sampling function itself, we start from an initial image and then repeatedly compute the gradient of the energy. Clamp it, take the Langevin step with noise, and clamp the pixels. Step 4 answers a very important question. Where do we start the chain? The choice of x0, meaning where we start in pixel space, matters enormously for how well our method converges. Let us consider the options. Option 1 is to start from pure noise every iteration. The chain would need thousands of steps to reach the low energy values, which is far too slow to run inside every training iteration. Option 2 is to start from real data points, which is classic contrastive divergence. This looks clever because the data already sits in low energy regions, so a short chain converges quickly. But there is a trap. If we start at a data point plus a tiny bit of noise, and the chain mostly drifts downhill, then the sample stays essentially equal to the data. That makes the data side and model side expectations equal, so the gradient becomes zero. But it's zero not because the model has converged, but because the positives and negatives are literally the same data points. Worse, the model only ever sees configurations near the data manifold, so the energy landscape far from the data, exactly where a generation chain from noise must travel, is never learned at all. Option 3, which is what we use, is a persistent replay buffer. We maintain a buffer of, say, 8,192 images initialized as pure noise. At every iteration, we draw the chain, initializations from the buffer, reinitialize a small fraction, about 5%, from fresh uniform noise, run a short Langevin chain of about 60 steps, and write the resulting samples back into the buffer. This solves both problems at once. First, the chains effectively mix for the entire duration of training. A buffer entry that keeps getting sampled accumulates thousands of Langevin steps in total, so the model samples genuinely come from the model distribution, while we only pay for 60 steps per iteration. And second, the 5% noise restarts keep the landscape honest. They constantly confront the model with noise-like configuration, forcing it to assign them high energy and to carve a traversable downhill path from noise all the way into the digit values. That's precisely what makes generation from pure noise possible later in step 7. In this code, this is the function that draws indices from the buffer, mixes in the noise restarts, runs the Langevin chain, and writes the samples back. Step 5 is the training loop, and here is the punchline. The cross-entropy gradient is just the data side expectation minus the model side expectation, and both expectations are now simply batch averages. The awkward option would be to assemble the gradient by hand. We could compute the gradient of the energy for every image in both batches, average them, subtract, and then manually write the result into every parameter's gradient field before stepping the optimizer. This works, but it's tedious, error-prone, and bypassed autograd entirely. So here's the convenient trick. The key realization is that an optimizer never actually looks at the loss value. It only looks at the gradient. So we don't need to hand autograd the true loss. We just need to hand it any function whose gradient with respect to theta happens to equal the formula we want. Then calling backward will fill the gradient fields with exactly the right numbers. Our candidate is a surrogate-loss, the batch average of the energy on the real data minus the batch average of the energy on the samples. When we differentiate this with respect to theta, the derivative passes straight through the sums, and we get exactly the batch estimate of the data side expectation minus the model side expectation. That is exactly the gradient we wanted. So backward does the hand assembly for us. But there is a trap here. When passing the derivative through the sum over model samples, we treated the samples as just fixed pixels independent of the theta parameters. And that's not quite right, because the samples were produced by a Langevin chain whose updates used the gradient of the energy. So the sampling process itself depends on theta. To account for this, we insert a detach on the samples in PyTorch, which cuts them out of the computation graph, so autograd sees them as constant tensors. We also add a tiny regularizer, alpha times the squared energies of the data and the samples, which keeps the absolute energy values from drifting off to plus or minus infinity. The reason is that without z, only energy differences matter, so the overall scale is unconstrained unless we pin it down. In the training loop, we draw model samples from the buffer, compute both energies from the contrastive loss plus the regularizer, and step the optimizer. And if you watch the printout, you'll see that the energy gap between samples and data stays small and hovers around zero. And at the end, we print the mean gap over the last 100 iterations as a sanity check with a warning that fires if the two energies ever look suspiciously identical. Now the question is, what do we watch during training? The most important diagnostic is the gap between the mean energy of the model samples and the mean energy of the real data. Early on, the buffer is full of noise, so the model samples should sit at visibly higher energy, which means the contrastive loss starts clearly negative. If instead the two energies are identical from iteration 0, the model samples are biased, and the model is not learning. Late in training, the gap should shrink towards 0 as the model distribution catches up with the data distribution. Step 6 shows that the energy landscape has learned to discriminate. We simply redo the digits versus noise histogram from step 2, and this time the histograms have split apart. The network has carved deep valleys in the 784 dimensional energy landscape, exactly where the real digits live. Step 7 is the fun part, generation, which is just rolling downhill from pure noise. Image generation here is just like dropping a new particle into a fluid and letting Langevin dynamics carry it into a valley of the energy landscape. We start from pure noise and run a much longer chain than during training, about 2000 steps instead of 60, saving snapshots along the way so we can watch a digit condense out of the noise. In the plots, you can see one Langevin chain evolving from noise into a clean digit, then a set of fresh samples generated from pure noise, and finally some samples straight from the replay buffer, which usually look the best since those chains have been refined across many training iterations. Compared to a diffusion model, this is a small and primitive setup, but conceptually we have just implemented the same pipeline that powers modern generative AI, a learned landscape plus a stochastic process that samples from it. Step 8 is a final sanity check on the energies of generated versus real images. If the model distribution really matches the data distribution, then generated samples should sit at energies comparable to real digits. So we compute the energies of the generated samples and overlay them on the real digit histogram. And you can see that the generated samples have found the same low energy values as the real data. And with that, I conclude this part of the EBM series. And here's a question for you. To train our model, we needed to sample new data from it. And since we did not know the partition function, it was quite challenging. There are methods to avoid sampling. How do you think those methods were? Write your answer in the comments below. And please send this video to someone who might find it useful. Your word of mouth is the best way to support me in creating more videos like this. And finally, I run a mentorship program where I can help you apply these models in your own projects, whether it's a portfolio project to boost your career or a business project to build a better product and increase your revenue. If you are interested, use the link in the description below to book a short call.